Hello everyone. After the state space equations, we will show the state space matrix form. So for that, we have a general representation which includes state vector, input vector or input matrix, and A and B represents the system matrix and the input matrix, which is represented by B. So for the output equations, y cx du can be written in matrix form. In that form, again, x represents the state vector, u represents the output vector, and c is the output matrix, D is the feed-forward matrix, and Y shows the output vectors of the system. Outputs can be anything related to the system according to our focus on the system. So these are the state space representation in matrix form. Now let's use that form in our last equations. What was the equations? X dot, the displacement first derivative, is equal to velocity, and the v dot, it is equal to 1 over mass minus kx minus bv and the applied force. So we obtained these equations according to our previous system. In the previous video, we obtained this state space equations. Now, to write the matrix form, first of all, we should clarify our state variables and the input, or if we have inputs. So state variables for the system, when we are writing the equations, actually we discussed this. Our state variables are x and v. So the displacement and the velocity are our state variables. So because of this, we wrote the first order equations for the state variables. So our state variable vector, which is x, which is used here, it's not displacement, can be written for the system as x and v, displacement and the velocity. And in addition to that, for the input vector, we have only one input for the system, which is applied force. After we determine our state variable vector and input vector, the remaining part of the matrix form representation is converting our equations into matrix form. So how we will do this? We will use this general representation. So we will start with x dot. X here represents the state variable vector. So x dot means our x dot and v dot will be on the left side of the expression. Then we have a matrix of A, input state matrix, which is A. Then X will come with the parameters of displacement and the velocity. Then we will use the B, input matrix, and finally U, which is FA here. Okay, so how we will decide the dimensions of A and B according to our state variables and the inputs. So for A, it must be equal to state variable dimensions. So if we have two state variables, the matrix A is a square matrix and it must contain 2 by 2 parameters. What about B? So for B, the rows of the B will be the state variable numbers, and then number of columns can be decided according to number of inputs. So we have one input, so because of this we have 2 by 1 matrix for B. Okay, now let's find the parameters of A and B, coefficients of A and B. How we will write? We will try to obtain these equations for the parameters of the A and B. So what we will do, we will obtain x dot is equal to v. So that means we have only one for that part. According to linear algebra, when you multiply 0 by x, 1 by v, and 0 by fa, you can obtain x that is equal to v. Similarly, to obtain the v dot, the velocity first derivative, we need minus k over m, which is the coefficient of x, minus b over m, which is the coefficient of v, 1 over m, which is the coefficient of fa for the second row. So we have the first part, state variable matrix form. But in addition to that, if we want to obtain an output equation or equations, we need to write this y is equal to cx du form according to our outputs. So let's say this is our general form, and let's say fk, v, and the acceleration of mass are the outputs as we discussed in the previous lecture. So here we need to find a matrix C, and matrix C dimensions will be number of rows according to number of outputs and number of columns according to number of states, because we will multiply this matrix with our state vector, which includes x and v. Then matrix D will come with the output number of rows and with the input number of columns, FA. So similarly, we can write C and D. For Fk, we should remember the expression is k times x for such a simple system because we have only one spring. So the first parameter, first coefficient will be k, the second one will be 0, and for the matrix D, we have also 0. So when you multiply the parameters coefficients to obtain Fk, we have k times x. What about v? V, it's our state variable, so only we have one here, but the remaining parameters coefficients will be 0. For the last row, the acceleration is equal to v dot, velocity first derivative. So when you check here, you can write the coefficients directly because we are trying to obtain the first same parameter, minus k over m, minus b over m, and finally 1 over m will come for the last part. So this is the output equations in matrix form, and here you can see the state space representation in matrix form. Thank you for watching.